We're going to take a look at another function, and we're just going to use the same information we've been working with in 4.6 to make a really good graph. So this function is a little bit different than one we've seen. It's 1 over 1 plus e to the negative x. So we're going to start with just our basic things like intercepts. So to find the x-intercept, we are going to plug 0 in for y. And when we do that, we multiply both sides by the denominator, we just get 0 equals 1, which that means there's no x-intercept. So that's it for that one. To find the y-intercept, we're going to plug in 0 for x. So we get 1 over 1 plus e to the 0. Of course, e to the 0 is 1, so our y-intercept turns out to be 1/2. So we'll put that in there. All right, the next thing that we want to find is, we could talk about the domain. That's going to be all real numbers. We can talk about asymptotes. Now, this is not a rational function, so the horizontal, vertical asymptotes, there are not any. But we can look at some end behavior to find out what's going to happen as we approach infinity or as we approach negative infinity, because that'll give us a good idea of what's happening to the left and right. So as we approach infinity, for this part, if we just think about the function e to the negative x, that's an exponential decay. So as that approaches infinity, it's getting closer to 0. So our limit is going to be 1 over 1 plus 0, which is 1. So our right-hand end behavior is going to be 1. I might do these. I'm going to put 1 right there. There. Okay. So to the right, that is what we're going to approach. Now, our left-hand end behavior, we have 1 plus e to the negative x. If we think about this exponential decay graph, as it approaches negative infinity, it approaches infinity. So this is 1 over 1 plus infinity, which is going to be 0. So our left-hand end behavior is going to be approaching 0. So I'm putting in kind of asymptotes there so you can see that. But that's what our left and right-hand end behavior is. As far as symmetry, I guess we didn't talk about symmetry yet. If we plug in negative x, we do not get the same thing back, nor do we get the exact opposite, so we do not have any symmetry in this graph. So there's not a whole lot of information here. We know about end behavior, and we've got 1 point. So to get more information, we're going to have to go to the first and second derivative. I'm going to need a new space to do this. So the first derivative, we are going to use the quotient rule. So we have low, and d high is 0. So low d high minus high. D low is e to the negative x times negative 1, because that's a chain rule, over the square of what's below. So this is just 0 times that. That's gone. So we have positive e to the negative x over 1 plus e to the negative x squared. And we want to set that equal to 0 to see where our potential critical values are. There's not going to be any places where this is undefined. And if we multiply both sides by the denominator, 0 equals e to the x, there is no solution to that. So we do not have any critical numbers. So no minimums and maximums. Now we can still plug into the first derivative. Just pick any number you want. I'm going to pick like 0. But when I do that, I'm going to get a positive number. Okay, so this tells me that this function is increasing on the entire domain. No minimums and maximums, it's increasing the whole time. So that's good to know, always increasing. I might go back and write that down, always increasing. And then we need to find the second derivative and see what we can find out about concavity. So again, I'm going to get a new space for this. So our first derivative, when it was all said and done, was e to the negative x over 1 plus e to the negative x squared. So now for our second derivative, we have another quotient rule. So we're going to do low d high, which is going to be negative e to the negative x, minus high. D low is going to be 2, 1 plus e to the negative x to the first. And then we need to do a chain rule. So that's going to be another negative e to the negative x. So that'll make this positive e to the negative 2x. I'm going to write that in there. Over the square of what's below. Now, from this step, we definitely want to factor out a 1 plus e to the negative x. And that is going to leave us with negative e to the negative x times 1 plus e to the negative x to the first plus 2e to the negative 2x all over 1 plus e to the negative x to the fourth. One of those will cancel. Okay, we're going to distribute and combine our like terms. So we get negative e to the negative x, and then I have negative e to the negative 2x, and that has a like term, so plus e to the negative 2x over that same denominator. Squeeze it in here. All right, pop back up here. I think I'm going to factor out a negative e to the negative x, which will leave me with 1 plus e to the negative x. No, 1 minus if I factor out a negative. Hang on. One minus e to the negative x all over 1 plus e to the negative x cubed. I'm getting kind of tired of e's by now. I may go one more step and drop that down into the denominator. So negative 1 minus e to the negative x over e to the x, 1 plus e to the negative x cubed. Okay, there's our second derivative. We want to set this equal to 0 and see if we have any potential inflection points. When we do that, excuse me, the only one we're going to get is 0. I don't have enough room to show you all that algebra, but 0. So then we're going to plug into the second derivative and see what's happening as far as concavity. So when we plug in something like negative 1, I think we get a positive number. And we plug in something like 1, we get a negative. So we can see that we're concave up before we get to the point 0 and then concave down after that, which means we have an inflection point at 0. We already have that point, 0, 1/2. Okay, so concave up and then concave down. So let's go back to our graph. We know that this is an inflection point. It's always increasing, but prior to this, it's concave up. So it looks like that, concave up, and then it switches to concave down. Okay, so that's what this is going to look like. And this is that inflection point.